The insulated grounding conductor for an isolated ground subpanel must be terminated at the transformer. According to National Electrical Code Section 250.32b, grounding means are required to be provided at any service over 1000 volts. The specific manner and extent of grounding will depend on the design of the transformer grounding used. In accordance with National Electrical Code Section 250.184, the grounded conductor of a three-phase system must be grounded at only one point in a building or structure. Given that a transformer grounding arrangement is already in place, it might be possible to connect the insulated grounding conductor to the existing grounding connection provided at the transformer enclosure. However, if the transformer is specifically an isolated grounding transformer, separate grounding means, such as ground rods, would then be necessary. It's crucial to thoroughly review the existing grounding details at the transformer location to ascertain the specific requirements for maintaining the desired isolation within the subpanel. The primary objective of an isolated ground system is to minimize electrical noise and interference that could potentially disrupt sensitive electronic equipment connected to the subpanel. This is achieved by providing a dedicated grounding path for the equipment, separate from the regular equipment grounding system. This dedicated path helps prevent unwanted currents and voltage fluctuations from propagating through the grounding network, which could otherwise compromise the performance and reliability of the connected devices. When installing an isolated ground subpanel, a key consideration is the proper termination of the insulated grounding conductor. This conductor serves as the dedicated grounding path for the isolated ground receptacles and equipment connected to the subpanel. To ensure effective isolation, it is essential that this conductor is routed directly back to the designated grounding point, which, in this case, is the transformer. By terminating the insulated grounding conductor, the transformer, a direct and uninterrupted path is established for any stray currents or voltage fluctuations to return to the source, minimizing the potential for interference and noise within the isolated ground system. The National Electrical Code provides specific guidelines and requirements for the installation and grounding of electrical systems, including isolated ground systems. These requirements are designed to ensure the safety and proper functioning of electrical installations, while also minimizing the risk of electrical hazards. Compliance with the National Electrical Code is essential for all electrical work, including the installation of isolated ground subpanels to ensure the safety of personnel and equipment. When working with electrical systems, it is crucial to prioritize safety and follow all applicable codes and regulations. Electrical work can be hazardous, and it is essential to take precautions to minimize the risk of electrical shock, arc flash, and other potential hazards. Always de-energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not qualified to perform electrical work, it is recommended to hire a licensed electrician who has the knowledge, skills, and experience to complete the job safely and effectively. The grounding requirements for services over 1000 volts are more stringent than those for low voltage services, due to the increased risk of electrical hazards associated with higher voltages. National Electrical Code Section 250.32b mandates that grounding means be provided at any service over 1000 volts to ensure the safety of personnel and equipment. These grounding means typically include grounding electrodes, such as ground rods or ground plates, which are connected to the service equipment grounding system. The size and type of grounding electrodes required will depend on the size and type of service, as well as the soil conditions at the installation site. In addition to grounding electrodes, other grounding means may also be required, such as bonding conductors and equipment grounding conductors. Bonding conductors are used to connect metallic parts of the electrical system together to ensure that they are at the same electrical potential. Equipment grounding conductors are used to connect the metallic enclosures of electrical equipment to the grounding system to provide a path for fault currents to flow back to the source. The design of the transformer grounding system is a critical factor in determining the overall effectiveness of the grounding system. The transformer grounding system must be designed to provide a low impedance path for fault currents to flow back to the source to ensure that protective devices, such as circuit breakers and fuses, will operate quickly and effectively to clear the fault. There are several different methods of transformer grounding, each with its own advantages and disadvantages. Some common transformer grounding methods include solid grounding, resistance grounding, and impedance grounding. Solid grounding involves connecting the neutral point of the transformer directly to ground. This method provides a very low impedance path for fault currents, which can help to ensure that protective devices will operate quickly and effectively. However, solid grounding can also result in high fault currents, which can damage equipment and cause voltage dips. Resistance grounding involves inserting a resistor between the neutral point of the transformer and ground. This method reduces the magnitude of fault currents, which can help to protect equipment and reduce voltage dips. However, resistance grounding also increases the impedance of the grounding path, which can slow down the operation of protective devices. Impedance grounding involves inserting an impedance such as a reactor or a resistor-reactor combination between the neutral point of the transformer and ground. This method provides a balance between reducing fault currents and maintaining a low impedance grounding path. The choice of transformer grounding method will depend on several factors, including the size and type of transformer, the voltage level, the load characteristics, and the desired level of protection. It is important to carefully consider all of these factors when designing the transformer grounding system to ensure that it will provide adequate protection for personnel and equipment. Maintaining isolation in a subpanel is essential for preventing electrical noise and interference from affecting sensitive electronic equipment. Isolation is achieved by providing a dedicated grounding path for the equipment, separate from the regular equipment grounding system. This dedicated path helps prevent unwanted currents and voltage fluctuations from propagating through the grounding network, which could otherwise compromise the performance and reliability of the connected devices. There are several techniques that can be used to maintain isolation in a subpanel. One common technique is to use an isolated ground receptacle, which has a separate grounding terminal that is not connected to the regular equipment grounding system. The insulated grounding conductor from the isolated ground receptacle is then routed directly back to the designated grounding point, which, in this case, is the transformer. Another technique is to use a shielded cable for the isolated ground circuit. The shield of the cable provides an additional layer of protection against electrical noise and interference. The shield should be grounded at the source end only to prevent ground loops. Ground loops occur when there are multiple grounding paths for a circuit, which can create unwanted currents and voltage fluctuations. To avoid ground loops, it is important to ensure that there is only one grounding point for each circuit. When installing an isolated ground subpanel, it is important to follow all applicable codes and regulations, including the National Electrical Code. The National Electrical Code provides specific guidelines and requirements for the installation and grounding of electrical systems, including isolated ground systems. Compliance with the National Electrical Code is essential for ensuring the safety and proper functioning of electrical installations. In addition to the National Electrical Code, there may also be local codes and regulations that apply to electrical installations. It is important to check with the local authorities to determine what codes and regulations are in effect in your area. When working with electrical systems, it is always important to prioritize safety. Electrical work can be hazardous, and it is essential to take precautions to minimize the risk of electrical shock, arc flash, and other potential hazards. Always to energize circuits before working on them, and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not qualified to perform electrical work, it is recommended to hire a licensed electrician who has the knowledge, skills, and experience to complete the job safely and effectively. The National Electrical Code, or National Fire Protection Association 70, is a regionally adoptable standard for the safe installation of electrical wiring and equipment in the United States. It is part of the National Fire Code series published by the National Fire Protection Association, a private trade association. Although the National Electrical Code is not itself a United States law, National Electrical Code is commonly adopted by states and municipalities in an effort to standardize their enforcement of safe electrical practices. In some cases, the National Electrical Code is amended with local requirements. The National Electrical Code is updated every 3 years. The principal sections of the National Electrical Code include Chapter 1, General, Chapter 2, Wiring and Protection, Chapter 3, Wiring Methods and Materials, Chapter 4, Equipment for General Use, Chapter 5, Special Occupancies, Chapter 6, Special Equipment, Chapter 7, Special Conditions, Chapter 8, Communications Systems, and Chapter 9, Tables. Annexes are not part of the requirements of this code but are included for informational purposes only. The National Electrical Code is a comprehensive document that covers a wide range of electrical topics. It is essential for anyone involved in the design, installation, or maintenance of electrical systems to be familiar with the National Electrical Code. The National Electrical Code is available for purchase from the National Fire Protection Association. It is also available online through various subscription services. The grounding details at the transformer are essential to determine what is required to maintain isolation in your subpanel. You'll need to examine the transformer's nameplate and any associated documentation to understand its grounding configuration. Look for information about whether it's a separately derived system, the grounding method employed, solidly grounded, impedance grounded, etc., and the location of the grounding electrode. Also, inspect the physical connections at the transformer. Note where the grounding electrode conductor is connected, the size of the conductor, and whether there are any bonding jumpers present. Understanding the transformer's grounding scheme is critical for ensuring that the isolated ground system in your subpanel is properly installed and functions as intended. This is because the isolated ground conductor ultimately needs to be connected to the same grounding electrode system as the transformer to provide a safe and effective path for fault currents. If the transformer is an isolated grounding transformer, it will typically have a dedicated grounding electrode system that is separate from the building's main grounding electrode system. In this case, you would need to connect the isolated ground conductor from your subpanel to this dedicated grounding electrode system. However, if the transformer is not an isolated grounding transformer, you may be able to connect the isolated ground conductor to the existing grounding connection at the transformer enclosure, as long as it meets the requirements of the National Electrical Code. Before making any connections, it's crucial to verify the grounding impedance to ensure compliance with code requirements. The impedance of the grounding path should be low enough to allow fault currents to flow quickly and safely back to the source, tripping the overcurrent protection device and clearing the fault. To verify the grounding impedance, you can use a ground impedance tester, which will measure the resistance of the grounding path. If the impedance is too high, you may need to add additional grounding electrodes or improve the existing grounding connections.